So today we are going to continue our discussion of feedback systems by talking about two of the improvements that we get by employing negative feedback. We're only talking about two today because Dr. Batari still hasn't finished the last chapter, and so I'm trying to slow down. With that in mind, the first thing that I want to talk about today is the concept of gain desensitivity. And to kick this off, we're actually going to work an example problem. So let's say that we have the following op-amp circuit. Here's R1. Here is R2. And here is our output voltage. We want to find several different things. So A, assuming infinite input resistance and 0 output resistance, we want to find expressions for our feedback factor K and our ideal closed loop gain. For part B, we want to know what values of K and R2 over R1 yield an ideal closed loop gain of 10 volts per volt. For part C, if our open loop gain for our amplifier is 10 to the 4 volts per volt, then we want to know what is our loop gain, our amount of feedback, and our not ideal closed loop gain using the results from part B. Not quite finally, D. What must K and R2 over R1 be to get AF is exactly equal to 10 volts per volt? And finally, E. If A1 decreases by 20%, what is the corresponding decrease in our closed loop gain AF. Okay. All right, so for part A, we kind of already know what these answers should be because we've dealt with a non-inverting op amp multiple times, but we will more formally do it from a feedback perspective like we did in class on Monday. So I can redraw my circuit using the practical op amp model where I have an infinite input resistance and a 0 output resistance. And so my circuit should look something like this. Here's my source voltage. There's my error signal. Here's my resistor R1 over which my feedback signal is applied. Here's my resistance R2. This is A1 VI. There is my output signal. So I know what my feedback signal is, I know what my output signal, I know what my source signal is, and I know what my error signal is. So I have all the different parts that I could possibly want if we were analyzing this guy from a system level. So from this, part A asks us to find our feedback factor, which is VF over V naught. And we can easily see that there is a simple voltage divider relationship between VF and V naught, much like we had in the last example that we worked on Monday. And so we would see that our feedback factor is, again, just R1 over R1 plus R2. And from this, our ideal closed loop gain is 1 over our feedback factor, which just looks like 1 plus R2 over R1, which is exactly what we would expect for an ideal op amp to have with this particular resistive feedback configuration. Yes, AF for the gain with feedback or the closed loop gain, and then ideal because the op amp is ideal. Yeah, nope. For part B, we were asked to find the values of our feedback factor and the ratio of resistances to get a closed loop gain of 10 volts per volt. So that means we have 10 volts per volt is equal to 1 over K. So from this, then K must be equal to 0.1 volts per volt. We also know that 10 volts per volt is equal to 1 plus R2 over R1, and therefore the ratio of our resistances, R2 over R1, must equal 9. Again, we haven't done anything that we couldn't have done with our simple ideal op amp analysis, excuse me, to this point. So for part C, we have a finite value for our open loop gain, and we're asked to calculate the loop gain, the amount of feedback, and the actual value of AF. So our loop gain, KA1, is 10 to the 4 volts per volt. That's our open loop gain times our feedback factor of K, which we know to be 0.1 volts per volt, gives us a value of 10 to the 3 volts per volt, or 1,000. Our amount of feedback is 1 plus KA1. So this would be 1,001 volts per volt or we'd call it about 60 decibels because that's typically the unit that we use for amount of feedback. Finally, our non-ideal closed loop gain is our open loop gain, A1, divided by our amount of feedback, 1 plus K, A1. So this looks like 10 to the 4 over 1001 gives us 9.990 volts, which is not approximately, actually, exactly 0.999 times AF ideal. So with our non-infinite open loop gain, we really only see that we have a decrease in gain by a factor of 0.1%. Okay, so and that's for not a particularly large open loop gain. All right, so part D asks us what value of K and R2 over R1 must be used to get a gain of 10%. And that was obviously what we were designing for. So what do we need to change to get that specific gain? Okay. So we know that our closed loop gain is our open loop gain divided by our amount of feedback. So that means we have 10 to the 4 over 1 plus K times 10 to the 4. I'm sorry. N is equal to that. Solving for K, we get 0.0999 volts per volt. We know that R1 over R1 plus R2, which is the expression for our feedback factor, is 0.0999 volts per volt. And we can rearrange and solve to find that the ratio of our resistances must now be increased to 9.01. And this will give us a closed loop voltage gain of exactly 10. Okay, so nothing, no too wild of a change or anything like that. Instead of using, say, a 9K resistor and a 1K resistor, we put our 9K in series with a 10 ohm resistor and we'd be good to go. So nothing too wild or crazy there. For part E, this is where things get a little bit interesting, okay? So in part E, we are told that our open loop gain is decreasing by a factor of 20%. And we want to determine what the corresponding decrease in our closed loop gain is, okay? So I want to hear some guesses as to what you guys think might be happening here before we mathematically show what's going on. This is gain desensitivity, okay? So we're changing our open loop gain by 20%. So we're lowering it from 10,000 to 8,000. That's a pretty appreciable decrease. Ballpark, what do you guys think is going to happen to the closed loop gain? It's going to decrease for sure. By how much do you think? Just make a wild guess. 40%. Okay, so that would make it very gain sensitive, not desensitive, right? So fundamentally, if this thing is working the way that we, if negative feedback is providing an improvement, we would assume that a change in the open loop gain would cause a smaller change in the closed loop gain, okay? So I'm going to say A1 prime is 0.8 times 10 to the 4 volts per volt, right? That's 80% of 10 to the 4. So from this, using the values from part D, our closed loop gain is going to be 0.8 times 10 to the 4 volts per volt divided by 1 plus our K value from part D, which is 0.0999 volts per volt, times our open loop gain, which is 0.8 times 10 to the 4 volts per volt. Again, and if we plug in these numbers, we get 9.9975 volts per volt. So from this, we saw that a 20% decrease in A1 yields only a 0.025% decrease in our closed loop gain. So we actually have quite a lot of gain desensitivity, okay? So our open loop gain decreased by 20%, our closed loop gain decreased by less than, so like 0.025 would be a 40th of a percent. 10. All right, so we have shown how gain desensitivity and all that kind of stuff works. Now let's maybe do a little bit better job of quantifying exactly what's going on, okay? If we use those exact two same resistors, absolutely. So we are saying we are applying the exact same feedback and the exact same amount of feedback. The only thing, or well, we're not applying the exact same amount of feedback. Let me be clear there, because the value of A1 has changed, but we're definitely applying the exact same feedback factor because the resistor values haven't changed at all, right? Okay. So we are literally just seeing what the effect of changing our open loop gain has on the performance level of our closed loop gain. And so with that in mind, where we're holding our feedback factor to be constant, we can develop a pretty simple relationship, okay? So we know that our our gain with feedback, or our closed loop gain, AF, is equal to A1 divided by 1 plus K A1. If we have a small change in our open loop gain, I can say that the derivative of both sides with respect to A1 should tell us what we are expecting to see, right? We're looking for the variation in the closed loop gain due to a change in the open loop gain. So if I perform this derivative, I get the derivative of my closed loop gain with respect to my open loop gain is equal to 1 divided by 1 plus KA1 squared. Okay. What I'm going to do now is just a little bit more mathematical manipulation in order to see, like, we can effectively develop a percent change relationship on both sides, okay? So if I multiplied both sides through by the change in A1, this would give me DAF is equal to DA1 divided by 1 plus KA1 quantity squared. And if I divide this equation by my original equation for the closed loop gain, what I get is DAF over AF, or the change in my closed loop gain, is equal to 1 over 1 plus KA1 times DA1 divided by A1. So I can see that that factor of 1 plus KA1, or 1 over 1 plus KA1, represents my desensitivity factor, right? So this says the change in the closed loop gain is equal to the change in the open loop gain divided by my amount of feedback. Okay. So we may also refer to 1 plus KA1 as a desensitivity factor as well as our amount of feedback, because it is increasing the desensitivity to variations in the open loop, changes in the open loop voltage gain. So let's look at another example. This one is kind of trivial. So let's say that we have an amplifier with a nominal gain of A1 is equal to 1,000 volts per volt, and it is exhibiting a change of 10% due to operating temperature variations. If we need to constrain the change to 0.1%, crap. By applying negative feedback, what is the largest closed loop gain we can achieve? Okay, so we have a trade-off here, right? We have an open loop gain of 1,000 volts per volt, but we know that it's going to vary by up to 10% as the temperature increases. If we want to minimize that variation by applying negative feedback, we should expect to see a trade-off, right? If the variation is reduced, we should expect to see the closed loop gain reduce as well. All right. So we know that we have the relationship, the change in the closed loop gain with respect to the closed loop gain, or divided by the closed loop gain, is equal to 1 over 1 plus KA1 times DA1 over A1. So to me, that looks like we have a 0.1% change in our closed loop gain is equal to 1 over 1 plus KA1 times the 10% change in our open loop gain. And so from this, we can easily see that our amount of feedback, or our gain desensitivity factor, 1 plus KA1, is simply 10% divided by 0.1%, or 100. And from this, our closed loop gain is going to be 1,000, our open loop gain, divided by our amount of feedback, or 10 volts per volt, okay? So to reduce that gain by a factor, that gain variation by a factor of 100, seems fairly obvious. We're going to reduce the we're going to reduce the open loop gain by a factor of 100 to accommodate that change, right? It is going to be a one-to-one relationship. All right, I have one more example problem on this topic that is a bit more involved, and it's specifically dealing with a very large change in the open loop gain, so that we cannot apply our differential relationship anymore because it's not valid if it's a large change. It's only for small variations, right? So I would say anything 20% to 25%. So like if we did the math for our previous example problem using the formula that we developed, we actually see that we would get a 0.024999 or whatever. So there's a little bit of variation there at 20%. When we're talking about a 50% change in the open loop gain, that error grows. The problem that we're about to deal with, the gain is going to change from 2 to 12. So that is a 600% change. So it's very obviously not going to be what we would consider a small change, okay? All right. Okay, so let's say we have a power amplifier employs an output stage whose open loop gain varies from 2 volts per volt to 12 volts per volt for various reasons. So temperature, manufacturing errors, etc. Not terribly important. What we are going to have to do to fix this problem and get things more stable is apply a preamp to drive this thing, okay? So I want to know what is the gain of an ideal non-varying amplifier so that an overall closed loop gain of AF is equal to 100 plus or minus 5% can be achieved, and what is the feedback factor that must be used. All right, so to understand this problem, I think it might be helpful to draw a schematic or a signal flow representation, okay? So what we have is a system that looks something like this. We're applying some input signal because it's a power amplifier. It literally could be voltage or current, so I'm going to leave it as X. We have our mixer here. Our error signal is being fed into our preamplifier. And so I'm going to say that it has a gain of A pre. And then that preamplifier generates the input for the power amplifier, which I'm going to call A power. And we know that this guy goes from 2 to 12 volts per volt. We want to know this guy's gain, and that combination of amplification, we are applying some form of negative feedback, as so, giving us our output signal of X naught, where our goal again is to figure out what the gain of our preamp needs to be and the feedback factor needs to be in order to make this happen. Now, again, we know that the change in our open loop gain for our power amplifier is very, very large. So it's going to increase by to be 6 times as much, right? So we cannot use our differential relationship. So to not use our differential relationship, what we're going to have to do is look at simply the closed loop gain of this amplifier system and then use that to go from there. So what is the closed loop gain of this amplifier system going to be? Can anybody tell me what it is? So I don't mean, I want an equation, okay? So what I mean by that is our closed loop gain, AF, for this system based on this signal flow diagram, what's it going to be? How does this differ from our generalized case that we were looking at the beginning of class on Monday? So we're not adding them together, we're multiplying them together, right? So it's 2 stages, 2 amplification stages cascaded together means we amplify the gains. Just like when we were cascading op amps together, stuff like that, okay? So our open loop gain for the system is then just A pre multiplied by A power divided by the amount of feedback, which is 1 plus our feedback factor times A pre times A power, right? Okay, so at the low end, when we have an open loop gain, excuse me, a closed loop gain of 100 minus 5%, that would just be 95, right? So we could say that 95 is equal to A pre times A power, so that would be twice A pre. I'm using the lower level for our power amp gain, divided by 1 plus 2 times K A pre. Anybody have any problems with where that came from? 2 is the gain of the power amp. At the upper end, we have 100 plus 5%, or 105, is equal to 12, which is our power amp gain, times our preamp gain, giving us our total open loop gain, divided by 1 plus 12 times K A pre. Okay, so what I can do, I have 2 equations and 2 unknowns. So I have a system of equations by which I can solve for both of these things. So let's talk about how we might go about doing that real quick. So I can say that 105 divided by 95, which is a nice scalar quantity, is equal to 12 A pre divided by 1 plus 12 Ka pre over 2A pre divided by 1 plus 2 A pre. And this is the same as 12 A pre over 1 plus 12 Ka pre. Sorry, I noticed that I did not include, this should be 2Ka pre. So when I divide by a fraction, it's the same as multiplying by a reciprocal. So that's going to give me 1 plus twice Ka pre all over 2A pre. And from this, I can see that I'm just going to have 6, because that's 12 A preamp divided by 2 A preamp times 1 plus twice Ka pre over 1 plus 12 Ka pre. And from this, then, I have 105 over 95 times 1 plus 12 Ka pre is equal to 6 times 1 plus 2 Ka pre. So if I consider the product of K times the preamp gain to be my variable, I can easily solve this guy and find that K times my preamp gain is 3.875. If I plug this value back into either my equation at the low end or high end, I'll get the same result. So I can say that 95 is equal to twice A preamp divided by 1 plus 2 times 3.875, which yields a preamp gain of 415.625 volts per volts. And from this, K, my feedback factor, must be 9.323 times 10 to the minus 3. And I get the exact same result if I use the 105 thing I checked just to make sure. So we've gone through the methodology of kind of having a little bit of a, not necessarily design problem in it, because we knew how everything had to be constructed, but we didn't know what the parameters were. So we would now need to design a preamp with this particular gain and set up a feedback system with this particular ratio in order to satisfy the design requirements of our overall system. And we've also looked at how to do this when the change in the open loop gain is small, or we could go the other way around and say we only have a small change in the feedback, so what kind of change in the open loop gain must have caused it, kind of thing as well. All right, so anybody have any questions with regards to gain desensitivity? All right, so then let us move on to bandwidth extension, okay? Now this is something that we've technically already covered. way back when we were talking about the constant gain bandwidth product of an op amp, but now we're generalizing it for really any amplifier circuit, okay? So let's say that I have a one-pole open loop amplifier. So that would have a transfer function A1 of S. So my open loop gain is going to be my mid-band gain divided by 1 plus S over omega high. So this would be valid for any system that has a dominant pole that tells us where our 3 dB cutoff frequency is in the high frequency response or anything like that, okay? Which is most of the things that we looked at previously with all of our transistor amplifiers. If we apply a negative feedback network where K is independent of frequency, so we have to make that caveat there. We can't have K involve capacitors or inductors because their impedances change with frequency, which means our feedback factor would also change with frequency. So if we apply only a resistive feedback network, then our closed loop gain as a function of frequency is going to look something like this. We would have in our denominator 1 plus our feedback factor of K times AM divided by 1 plus S over omega high. And in our numerator, we would just have AM divided by 1 plus S over omega high. And I'm going to multiply through by 1 plus S over omega high to kind of clear some fractions out here. This is going to give me AM divided by 1 plus KAM plus S over omega high. Looks fine. I'm going to do one other thing, and the reason for it will be obvious momentarily. I'm going to multiply this guy by a factor of 1 over 1 plus K AM over the same thing. So effectively, I'm factoring out a common factor of 1 plus K AM there. And this is going to give me AM divided by 1 plus K AM divided by 1 plus S over 1 plus K AM times omega high. Okay. This is an interesting result. Okay. So what is happening to our mid-band gain? So let's ignore this whole denominator for right now. What's going on with the mid-band gain by applying negative feedback? We're reducing it by a factor of the feedback applied, right? Nothing wild or crazy there. That's exactly what we got previously. What's happening to the location of our pole frequency? It's being multiplied by that exact same factor, okay? So we see that in a, we can use negative feedback to extend the bandwidth of our system by moving our pole from one location out to a location that is a factor of 1 times K times the mid-band gain away. So we lower the gain and we extend the bandwidth, but we are maintaining a constant gain bandwidth product, okay? So this is a more formal description of really what we already knew, but now we have a specific mathematical relationship for it, okay? So let's work I think we have time for two examples. The first one is, again, rather trivial, and the second one's going to require a little bit more thought, as was the previous case, okay? So let's say that we have an op amp with a DC open loop gain of 100 decibels. So I'm going to call A midband 100 decibels, which is the same as 10 to the 5 volts per volt. It has a uniform minus 20 decibel per decade gain roll off. That's just a fancy way of saying it has one high frequency pole, right? And that frequency occurs at 100 hertz. So F high, and I'm going to specifically say at 100 decibels, is 100 hertz. We want to know what amount of feedback and what feedback factor is required to get a DC closed loop gain of 20 decibels. So that means that our AF is 20 decibels, which is 10 volts per volt in a linear scale. And we want to know what the bandwidth of our new configuration is, okay? So using this information, we know that our closed loop gain is 10. So 10 must be equal to our DC open loop gain of 10 to the 5 divided by 1 plus K times 10 to the 5. So from this, our amount of feedback applied is 1 plus K AM, which has to be 10 to the 4th by inspection. Everybody okay with that? So 10 to the 5 divided by 10 to the 4 gives me 10. So I know what my amount of feedback applied is. And since I know that, I can easily determine my feedback factor of K. So it's going to be 9.999 times 10 to the minus 2, right? I know that, let's see, 10 to the 4 minus 1 is equal to K times 10 to the 5, and then I solve for K. So nothing wild or crazy there. Okay, so we see what our closed loop gain is and all that kind of good stuff. We've reduced it by a factor of 10 to the 4, which means we have extended our bandwidth by a factor of 10 to the 4. So our new high frequency cutoff at 20 decibels is simply 1 plus K AM times our old high frequency cutoff, which occurred at a gain of 100 decibels, is 100 times 10 to the 4 is 1 megahertz. All right. So again, if we decrease the gain by a factor of 10,000, we have to increase the bandwidth by a factor of 10,000. Nothing remotely difficult there. That is the level of understanding that you have to do the homework and do these problems on an exam or something like that, okay? Now, let's make things hard. Or harder. I wouldn't even classify this as particularly hard, okay? This is more of a design problem, all right? All right, so we are trying to design an amplifier with the following parameters. A gain of A and I'm going to say mid-band gain of 1000. And we have a 3 dB cutoff frequency F high of 1 megahertz. Okay. What we have available is an amplifier with an open loop gain of 1000. But it has a dominant high frequency pole at 20 kilohertz. So what we are going to be investigating with this problem is cascading closed loop amplifiers together to achieve the same gain, but with a much higher bandwidth, right? Getting from 20 kilohertz to 2 megahertz means we have to lower the gain of a single stage very appreciably, right? But we can get to this high gain constraint by just cascading these guys together, okay? So I want to know how many of these guys we have to cascade together. And also, we are told that the 3 dB cascade frequency is equal to the 3 dB stage frequency times a factor of the square root of 2 to the 1 over nth power minus 1, where n is the number of stages. Okay. So we know that one stage isn't enough because we obviously don't meet the bandwidth requirement. So somebody take a stab in the dark and tell me how many stages you think this is going to take. Three. Okay, anybody got a problem with 3? Well, congratulations, you guessed the right answer on the first go. But it'll be okay, we'll prove it, all right? So for n is equal to 3, our gain with feedback per stage. How might we go about figuring that out? Not a trick question, okay? So we have 3 stages cascaded together, right? And we know that the overall gain of this system needs to be 1000. So I would argue that the gain with feedback, or the closed loop gain that each stage needs to provide, is the cubed root of 1000, right? Because we're just going to multiply those 3 stages together. So that would be cubed root 1000, or 10 volts per volt. Okay? So in order to achieve a gain reduction from 1000 to 10 volts per volt per stage, how much feedback, like what is the amount of feedback that we need to apply? Well, we know that 1 plus Ka1 is equal to Am over AF, right? And in this case, that's AF stage. So that would be 1000 volts per volt divided by 10 volts per volt, which would give us 100 as our amount of feedback. And from that, KA1 must be 99, and therefore the feedback factor that we are applying to all of our three identical stages is K is equal to 0.099 volts per volt. All right. So we know that under these constraints, this is easily doable, right? We're going to have three stages with a gain with feedback of 10 volts per volt. Now we need to figure out what the extension of the bandwidth is when we do this. So each stage, F3dB stage is going to be 1 plus KA1 times our high frequency pole value. So that is going to be 100 times 20 kilohertz, looks like 2 megahertz to me, okay? So now we're going to chain those three stages having a gain of 10 volts per volt, but a bandwidth of 2 megahertz together. And so what that's going to give us is a 3 dB cascade cutoff frequency of 2 megahertz times 2 to the 1/3 power minus 1, which is 1.019 megahertz. So pretty dang close to our design criterion frequency. We only did two stages. We'd actually come out at around 640 kilohertz, which is well below our cutoff frequency. If we did 4 stages, we'd wind up somewhere closer to 2 megahertz for the overall system, which is well beyond what we were explicitly asking for. So 3 is the magic number based on how these amps behave. So very good guess. Yeah, and then you have to do an iterative process. You either got it right. So if you overshot it, you would go down in the number of stages. If you undershot it, you would increase the number of stages. Yeah. But so all the math that we did here is dependent on all of the gauge stages, the gain stages being identical. Okay. So this situation is, just to be clear here, XS mixer gain stage feedback into another mixer gain stage negative feedback into another mixer gain stage. Here's our output. That's not where that's supposed to go. Feedback like so, where all those A's are identical and all those K's are identical. If we don't have that constraint, the way that we approach this problem does not work. So I just want to be clear about that. All right, that's all I had prepared for today. So we're getting out about 15 minutes early. So, all right. You should be good to go doing homework problem 1 and homework problem 2. And based on the difficulty of example problems and stuff that I've worked, they should be ludicrously trivial to you. So.
Probably a stupid question. We just A1 is A1.
Yes, is our mid-band gain, because we're looking at this guy as a high frequency, or as a, I don't want to say a filter circuit, but kind of as a low pass filter circuit. Our mid-band gain is our DC open loop gain, which is what we were dealing with earlier with the A1. Whatever. Yeah. So 4 different conventions to deal with. Mine is right.